Hey everyone, this is Eric. Today I want to talk about APMO 2011 Problem 1. APMO stands for the Asian Pacific Math Olympiad, which is an annual math competition for high schoolers around the world, where the students have 4 hours to solve 5 proof problems. This was the first and easiest problem on the test in 2011. The problem asks, let A, B, C be positive integers. Prove that it is impossible to have all three of the numbers a squared plus b plus c, b squared plus c plus a, c squared plus a plus b to be perfect squares. Here, perfect squares are numbers that can be written as the square of an integer, like 1, 4, 9, 16, and so on. So we want to prove that it's impossible to have all three of these expressions be the square of an integer. The solution to this problem is quite tricky, so instead of just telling you the solution, I'm going to go over the motivation for how someone might come up with a solution. If you want to try this problem for yourself, feel free to pause the video. How do we approach this problem? Let's first try some examples to get a feel for what's going on. Start simple. Say a, b, and c are all equal to 2. When we plug this into the expressions, the three numbers we get are 2 squared plus 2 plus 2 equals 8. 2 squared plus 2 plus 2 equals 8, and 2 squared plus 2 plus 2 equals 8. 8 isn't a perfect square, so none of the three numbers are perfect squares. Let's try a few more examples. If a, b, and c are all 3, then the three values are all 3 squared plus 3 plus 3 equals 15. If a, b, and c are all 5, then the three values are all 5 squared plus 5 plus 5 equals 35. 8, 15, 35. There seems to be a pattern here. 8 plus 1 equals 9, 15 plus 1 equals 16, and 35 plus 1 equals 36. All of these numbers are 1 less than the perfect square, but not the perfect square itself. What's going on here? In all our cases, a equals b equals c. When this happens, we can rewrite everything in terms of a. So all three values become a squared plus a, which is a squared plus 2a. If we add 1 to this value, we get a squared plus 2a plus 1, which happens to be a plus 1 squared. So our three values are all 1 less than the perfect square. What a coincidence! The problem wants us to prove none of these three numbers are perfect squares, and they all happen to be 1 less than the square. Those cheeky bastards. So we know that when a, b, and c are equal, we're supposed to get 1 less than the perfect square. Let's take a closer look at what's going on, using 5 as our example. Our three numbers in this case are all 5 squared plus 5 plus 5 equals 35, which equals 6 squared minus 1. As we said earlier, we're just shy of 6 squared. We can picture this equation geometrically. 5 squared is the area of this 5 by 5 square, and the two individual 5s represent the areas of this 5 by 1 rectangle and this 1 by 5 rectangle. Now we have a 6 by 6 square missing a block in the corner. That means that the blue area is 5 squared plus 5 plus 5, and it's also equal to 6 squared minus 1. Alas, we fail to fill up the square. We started from 5 squared and added on 2 5s and barely didn't reach the next perfect square. Dang it, we're literally so close. If we just add 1 to these three equations, all these 35s would be 36s, meaning we get our three perfect squares and the problem statement is wrong. You know what? Let's see if we can make the problem statement wrong. I don't believe it's true. I think we can make all three values perfect squares if we just choose a, b, and c correctly. If we look back at our equation, all we had to do was add 1 to turn the 35 into 36. So let's add 1. Let's change this 5 to a 6. So a and b are still 5, but now c equals 6. Then our three numbers become 36, 36, and 46. Well, we did better than before. 2 of the values are squares, but 46 isn't one. It's somewhat close to 49, which is 7 squared, but it doesn't quite reach it. Let's use our diagrams again to visualize these equations. This time, the first two equations do give 6 squared. The last bit was filled in when we changed one of our 5s to a 6. But in the last equation, we now start from a 6 by 6 square and add on a 5 by 1 and a 1 by 5 rectangle. Our goal was to cover this 7 by 7 square, but the two rectangles can't even cover an edge of the 6 by 6 square because, well, 5 is less than 6. Okay, let's keep trying. We can't lose hope because of one example. We have to prove them all wrong. But this time, we'll choose our numbers more carefully. We have to start somewhere, so say a equals 5 still. Then the three expressions are 25 plus b plus c, b squared plus c plus 5, and c squared plus 5 plus b. As before, let's say 25 plus b plus c equals 36, so we know for sure that at least one of these values is a square. That tells us b plus c equals 11. Last time we chose b equals 5 and c equals 6, which didn't work. Let's try some of the other values. Actually, no. Let's try all of the other values. It doesn't make a difference whether b or c is bigger, so let's just assume b is less than c. Then our options are ABC is 556, 547, 538, 529, and 5110. As we said earlier, the first one gives 36, 36, and 46. We can calculate all the other values pretty easily, making sure not to make mistakes. Unfortunately, none of the examples result in 3 perfect squares, and only one of them results in 2. 5, 110 gives us 36, 16, 106. Let's take a closer look at the last example here. Again, the first two values are squares and the third one isn't one. For the third value, we started from 10 squared, which is 100. So in order to get to the next perfect square, our goal is 11 squared, which is 121. 106 is just so far away. 5 and 1 are not enough to get us there. Maybe the problem is that when a and b are too small, it's impossible to reach the next perfect square. If we look at our diagrams again, 16 and 36 don't really fit into a neat picture. But the diagram for 106 shows just how far away we are from reaching our goal. We don't come anywhere close to filling in the 11 by 11 square. The 1 and 5 don't even make it halfway to the end of the 10 by 10 square, let alone filling in the rest. A and b would need to be a lot larger for 100 plus a plus b to be a perfect square. Wait, how large exactly? We needed to reach at least 11 squared, which is 121. So 100 plus a plus b is at least 121, which means a plus b is at least 21. Right now, a plus b equals 6, not even a third of what we want. It just requires so much to reach the next perfect square. If we try to look for more examples, we keep on running into the same story. It's not too hard to make two of the values perfect squares. For example, if a, b, c equals 3, 3, 4, the numbers we get are 16, 16, 22. If a, b, c equals 3, 6, 10, we get 25, 49, 109. If a, b, c equals 6, 11, 17, we get 64, 144, 306. But the last value, the largest value, always doesn't work. It's always c squared plus a plus b that's not a perfect square, because in all our examples, c is the largest. So, what happens exactly when c is the largest value? Equality is allowed, so a is less than or equal to c, and b is less than or equal to c. Is it possible for c squared plus a plus b to be a perfect square? Let's look at our diagram again for inspiration. This time we're starting from a c by c square, and we're adding on an a by 1 and a 1 by b rectangle onto the edges. Because a and b are both at most c, we might cover the full edge of the square, but we won't extend past it. That means that, like in all our previous examples, we cannot cover the corner block, so we cannot fill in the full c plus 1 by c plus 1 square. How does this translate algebraically? The whole point of this problem is that there are no perfect squares between c squared and c plus 1 squared, because there are no integers between c and c plus 1. So if our value is a perfect square, it must reach at least c plus 1 squared, meaning c squared plus a plus b has to be at least c plus 1 squared, which equals c squared plus 2c plus 1. However, since a is less than or equal to c, and b is less than or equal to c, c squared plus a plus b is less than or equal to c squared plus c, which equals to c squared plus 2c. These two inequalities can't both be true. So when c is the largest, c squared plus a plus b cannot be a perfect square. But c doesn't have to be the largest. What if a or b is the largest? The thing is that the problem is symmetrical, so we can just use the same logic. If a is the largest, then b plus c is less than or equal to 2a, so a squared plus b plus c is less than or equal to a squared plus 2a, which is less than a plus 1 squared. So a squared plus b plus c can't be a perfect square. If b is the largest, then c plus a is less than or equal to 2b. So b squared plus c plus a is less than or equal to b squared plus 2b, which is less than b plus 1 squared. So b squared plus c plus a isn't a perfect square. Therefore, regardless of whether a, b, or c is the largest, at least one of the three values is not a square. So it's impossible for all three values to be a square. To sum everything up, let's write a proof for this problem like we would on an actual contest. In our proof, we're not going to deal with separate cases where a is the largest, or b is the largest, or c is the largest. Instead, because all three cases are essentially the same, because the problem is symmetrical with respect to a, b, and c, we can just assume that c is the largest and say that the proof is the same for the other two cases. This is called without loss of generality, or WLOG. So, proof. Assume without loss of generality that c is the largest, that a and b are both less than or equal to c. Then, c squared is less than c squared plus a plus b is less than or equal to c squared plus 2c, which is less than c plus 1 squared. That forces c squared plus a plus b in between two consecutive squares, so it's impossible for c squared plus a plus b to be a perfect square. And that's it! Thank you all for watching, and see you in the next video.